Cool. Hey, welcome everyone. Thanks for coming. I'm Akshay. I'm a Google developer expert for Android and Kotlin. I like National Park, as you can see from my emoji there. And I work at Tinder along with Tasha here.
Hey everyone, I'm Tasha. I also work at Tinder with Akshay. And according to my emoji, my whole personality is that I have a cat named Spooky. All right, so we're really excited to share this talk with you guys today. It's just a bit of a preface as to why we're giving this talk. So at Tinder, we've been gradually integrating Compose only in new features. And we've noticed that it's actually really easy to write non-performant code in Compose. So you have a lot of factors working against you. It's a brand new framework, a new way of thinking, and on top of that, code that may look fairly innocent can actually cause a lot of UI jank unintentionally. And fixing performance issues in general is a huge hurdle. First of all, it's hard to know where to start, and then it's also hard to know if you're on the right track. So today we have a live debugging session lined up where we're going to look at a Janky app and try to fix some performance issues live, and hopefully that goes well. So to start us off, Akshay is actually going to introduce the app that we'll be looking at today. So take it away.
Yeah. So in order to explore these ideas further in a sandbox environment, we built off a clone of the Tinder app, and we call it Janky Tinder. And this app is we built this fully in Compose, and so this allowed us to explore how jank could seep in as you added more features, added more layers of code, and you kept on building on top of it. So we added essentially 3 screens to this app. So the first one is card stack, similar to the real Tinder app. And here you can swipe on cats, though. And the second screen we added is a match list, where you see all your matches and you can message them. And the third screen we have is the profile screen. And so yeah, our task here, our Jira ticket, is to fix the janky card swipes. And so what's wrong with the app right now? There are super laggy card swipes. And there is a huge jank when you try to drag the card around. And so the acceptance criteria of this ticket is to have smooth card swipes and have butter-like card drag. So with that in mind, Tasha, should we check how the performance is at the moment, right?
Absolutely. So as I was just showing a second ago, so when I try to pick this card up here and drag it, it's kind of slow. It's not the best. And in fact, it's not that responsive to me sort of dragging it really fast. So we really want to try to see if we can quantify this jank here, because we can kind of see and I can kind of feel physically when I use the device that there is a delay and it's not that responsive. And ideally, in a production app, you might have some analytics in the wild that give you a good idea of how your features or your screens are performing in the wild, across a plethora of devices and user scenarios. But while debugging issues, you want a quick local signal to kind of quantify the jank you're seeing with your naked eye. So in order to do that, we're going to take a look at the macro benchmark library, and we're going to use that library to automate essentially this action that I was doing, dragging the card around, and we're going to measure a specific metric that will give us some indication as to how the frames are performing. So we're going to take a quick look here. This is a preview of a test we wrote earlier, and the test is called drag card around. And what we're going to be doing is essentially automating, holding onto a card and dragging it around slightly. So the video on the right shows you what it looks like when the test is running on device. And the way this interaction works is we're using a UI Automator API, which is similar to Espresso. If you're familiar with that, we grab the resource ID of the top card and we drag it around. And then specifically, we're measuring the frame timing metric. And that's going to give us some indication into how the frames are performing. So with this quick preview, we're going to jump to Android Studio. Actually, going to take us into the test.
Sounds great. So yeah, since Tasha showed us the test, we have already run this test just to save some time. So ideally, when you create the benchmark test, it will live its own module. And when you run the test, it will generate a JSON file, which is in build outputs. And it goes under connected Android test folder. And usually it has the name of your device. So let's just jump into the JSON file. And it has a bunch of numbers. But the 2 key things we want to look at is the frame duration CPU, which indicates the duration the CPU takes to process a frame on both the UI and under thread. But more than that, the most important one is the frame overrun millisecond in our case. And here it measures how much a frame has exceeded or missed its rendering deadline. So any positive value here indicates dropped frame and jank. So if you see a positive value, definitely there's a jank and missed frames. And if there's a negative value, that means that it was an early completion. Ideally, you would want your values to be 0 or in negative, or for sure less than 16 milliseconds, because after 16 milliseconds, the user starts to see a bunch of lag over there. So if we jump back to the test which Tasha was showing, so there was one more thing to note with Compose. Since we are using the UI automator framework, if you have used it before with XML, you usually have resource IDs helping you to find the element so that it can find the card and you can drag it around. But for Compose, since there is no resource IDs, you need to use something called as semantics. So it's a modifier semantics, and so you just need to say test tags as a resource ID true. So what that does is, like any test tags you add, they will be converted as resource IDs. So one thing to note is that you just need to do the semantics once at the top of your tree node. So probably potentially your parent composable. In our case, it's the scaffold one. That's where we added it. And after that, you just need to add test tags everywhere where on the composables which you want to interact with in the test. So yeah, now that we can quantify the jank somewhat, let's see what the issue is and where this jank is coming from.
Okay, so with the numbers in mind, we're actually going to take a look at our first tool, and that's going to be the Studio Profiler. So this might be familiar to most of us here, and we might have used this before. And with the profiler here, what we're going to do today is essentially take a trace and perform the drag interaction and see what's going on, see if we can't figure out or pinpoint where the jank is happening. So we're attached the process here, and we're going to hit the CPU section. Now, this might be also familiar to most of us. We have two kinds of traces that we're going to look at today. The first one is the system trace, also known as Systrace. Might have used this from the command line as well. So the Systrace is going to give us a general overview of how the app is interacting with system resources, CPU information, render information, things like that. So it's kind of a wide net. It's not going to really pinpoint where your issue is, but it's going to give you somewhat of an idea of what's happening. The other one is the method trace. The method trace is actually going to tell you timing information for every method that's running as you're interacting with the app. So as you can imagine, it's super fine-grained, but that comes with a lot of overhead. In fact, if we did try this today, we'd barely be able to interact with the app, much less parse the trace and look at it together. So in order to really pinpoint where this lag or jank might be coming from, we need something that's the best of both worlds. And to the rescue arrives a nice little library called the Composition Tracing Library. So this is the artifact here. We've included it already. It's in beta, I think, at the moment. And this library is really cool because behind the scenes, it attaches trace calls around every composable. So when you run a regular system trace, you get low overhead, but you'll also be able to see detailed information about what composables are running, how long they're taking to run, and all that good stuff. So we're going to go right ahead and actually run a systrace with this already attached. I'm going to hit record, and then I'm going to drag this around a little bit. I'm going to stop. And once we stop here, hopefully we can get a system trace.
Classic Android Studio.
Classic. Okay, but luckily, this will happen in practice, but luckily we did have a trace saved from earlier. So typically when this does work, it will stop, and you'll be able to see a little a new element over here with a little save icon. And that's essentially the trace file. And you can save that to anywhere on your computer and then open it up in a tool called Perfetto. So you can view the trace in Android Studio, but the better way of doing it and the easier way of navigating around the trace is going to be via Perfetto. So any trace that you capture in Android Studio can be opened up here. So this was a trace that we ran earlier with the same interaction of dragging the card around. So when you load up your trace file, you want to find your process or package name. So our package name is Goofy Goober. That's a SpongeBob reference, if anyone knows. So this is our process, and this is the trace. So two kind of sections to really pay attention to here. The first section is the expected timeline. This is going to basically tell us what the system thinks should be happening and when frames should be produced ideally. The second row here is the actual timeline. And this is how the frames are actually being produced as I drag the card around. Ideally, you would see a lot of green squares here, but clearly there's nothing expected happening, and it's all pretty bad. So we're just seeing a bunch of orange rectangles. So this is one indicator that you do really have a lot of jank. So even if you might not be able to notice it with the naked eye, just running this trace gives you an indication. Now, if we go here and zoom into the process name, we can actually see more information about actually the composables that are running. So let's see if I can zoom in a little bit. So card stack is actually the name of a composable that we have. So as you can see, this is actually just taking a long time to run. I mean, we barely see the end of this rectangle. If we zoom in a little further, we're going to see a ton of these tiny little rectangles. Keep going in, and then we'll see something interesting here. We'll see the name of other composables. So if we zoom out, paying attention to this swipeable card here, if we zoom out, we're actually seeing a ton of swipeable card composables being created or recomposed or something like that. We don't really know what, right? But we really only see one or two cards on the screen at a time. So I don't know why this is happening, and I don't know what to do about it.
I can help you with that. Let's see if we can figure out like what's happening here. So if we go back to Android Studio, stop this if it can even stop. And then, maybe let's use Layout Inspector to see what is happening under the hood. Since Tasha mentioned that there are like a bunch of instances of swipeable card getting generated, maybe let's see if they're also rendered on the layout. So swipeable card, we can search here. And it seems that there are like a ton of swipeable card here. I don't know why. Ideally, like we would just want a couple of cards on the card stack and they just are like recycled. But for some reason, there are like a bunch of them generated. So let's see into the source code and what is happening here. So we have a swipeable card, looks pretty easy. Then we have something called is card visible. Maybe that's something related. Let's jump in. So this looks like a business logic. So we have a logic which says only the first, second, or the third card should be visible at a time. So essentially only 3 cards should be visible. But for some reason, we have like hundreds of them. So let's see what's happening. So the business logic is correct. But we are passing this to something called as visible, which is our own custom modifier. So what we are doing here is measuring and also doing a place. The only thing is that for some reason, we are doing this, this measure phase, even if the card is not visible. So I don't know, the placing looks correct. I think that we are doing this measure phase for all the cards which are there, even if they are visible or not. So maybe we should like try moving this inside. So essentially when the card is visible, then only we measure it. So let's run and see if that makes a difference. So let's hold on while it builds and loads. Oh, cool, yeah. So swipeable card, let's search for that. And lemon drizzles, we only have 3 swipeable cards now. And looks like that should have done it. But let me explain like what just happened here. So if we jump back to the presentation. So as you know, like Compose has three main phases to draw something. So composition, layout, and drawing. And the layout has 2 phases, measure and place, which we just saw in the visible modifier. So what happens during the measure phase is Compose takes your UI and measures the width and the height needed for the further stages. So what was happening in our case, that we were doing this measure phase for all the cards, right? So what was happening is that Compose was measuring the height and the width for all the possible cards to show on the screen. And as soon as we moved this inside the visible block, what happened was it was just doing the measure phase only for the 3 cards we want to show. And then other things continued the same. So in the place phase, what Compose does is it just takes this card and places them on the screen. So yeah, let's go back to Android Studio. And yeah, that looks good. I think we can ship this and end the talk. But yeah, like before that, maybe just do our due diligence, like before QA checks this out. Let's try to see if the performance is good or not. Okay, I mean, I still see some jank. I mean, I don't think you are able to even see it. It's that slow.
Oh, wow.
And there is like some weird number which keeps rising up. Tasha, do you have any idea what that number is about? Seems seems bad. I mean, the performance is still bad, but there's some number. Oh, wow, it's like 50 or 60 now.
Yeah, this is crazy. I mean, I'm not even swiping the card. I'm just like dragging it around. I don't know what's happening here. Let's actually see what this column says. Okay, 192. That doesn't sound good. Okay, so this column indicates the number of times this composable has been recomposed. And I think we all know what that means. We're going to talk about recomposition.
Yeah, our favorite topic.
So before we actually dive in, just to note, like this is actually happening, some of this jank is kind of coming from the layout inspector itself. Like it's actually not showing as responsively as it's showing on the device right here. So that's just one thing to keep in mind. But as soon as I let go and layout inspector refreshes its stuff, we still see the numbers go up. So not good. All right. So as Akshay mentioned, we were talking about the sort of 3 phases that Compose goes through. So let's take some examples of a couple of frames and see if Compose thinks it should run all those phases all the time. So let's say on frame 1, the UI is running for the first time, and Compose is thinking, okay, let's just render everything. We'll run through all the phases for the first time. Then let's say that before the next frame, a change comes in where a new rect is drawn on screen. At this point, there's no change to the UI tree. No positions or measurements have been changed. Just something new has been drawn to screen. So at this point, on frame 2, the system might say, OK, well, let me not just run the composition and layout phases, because the only thing that's changing is a draw operation, essentially. Then let's say that before frame 3, another change occurs where we introduce a text element in the UI tree. So at this point, the UI tree itself is changing, a new element has been added, so we would want to run all 3 phases because we want to render this new element on screen. So in this case, Compose might not skip anything at all. Final example, before frame 4, let's say another change comes in that's going to change the position of an existing element on screen. So in this case, we're not adding new elements to the UI tree, we're just changing the position of an existing element. So here, the composition phase might be skipped. And this is a very simplistic view of how things work under the hood, but it's kind of a high-level bird's-eye view, and it's good enough for us to kind of reason about the fact that performance issues are usually happening because Compose thinks it needs to run all phases all the time whenever there are even the smallest of changes. And the job of kind of reducing performance issues really lies in helping Compose out and really giving it the signal so that it can skip these phases when they don't really need to occur. So let's actually jump back to swipeable card and see if we can spot where extra recompositions are happening. So we click directly from the layout inspector, which is cool. OK. Swipeable card is called here. Not too many parameters, doesn't look too crazy. There's some logic happening here. Here was our test tag that we used for the test. Let's click into swipeable card. This looks pretty simple. It's a card. We got some modifiers. I mean, there's not much else going on. And I think, like, at first glance, I'm stuck. Like, I can't pinpoint where recompositions we have.
Yeah, I mean, tell me about it. Like, for days, I have been baffled by these performance issues. Compose, and nights have turned into sleepless nights. But just one faithful night, I stumbled upon something, a hidden treasure, this secret book of Compose performance. And literally, this book had like a dedicated section on debugging this recomposition issues. And like, I just immersed myself in this wisdom shared within this book. And the first few pages it had was, go for it. It said, use Lambda versions of modifiers for frequently changing data. So what that means is, like as Sasha showed, we have this swipeable card and a card internally. And we are setting some modifiers on it, like specifically the offset and the graphics layer. So what's happening is that when these values change, Compose, so we are like setting some values on this, and these values are changing. So whenever these values change, Compose thinks that the whole tree has changed. So it invalidates the card and the swipeable cards as well. So the whole thing is recomposing. So essentially, like Compose thinks that these modifiers are immutable, and when we change something here, it needs to think that the whole UI tree is changing. And the other thing which the book said again, this is like a whole section on debugging recomposition. So the second thing it said was defer state reads as long as possible. And what that means is, so as you saw when Tasha was showing that we have the swipeable card, and we are doing like bunch of state read, just straightforward, nothing bad there. We are just, there is a state, we are passing it, and we're just reading some values from there, and just passing them to the swipeable card. Nothing wrong here, right? But not for compose. Compose thinks that this state is being read here. So it thinks that, okay, the state is being used, so I need to like keep an eye. So to keep an eye, it just takes the whole thing. Like it thinks that the whole card stack and the swipeable card is the recomposition scope. So it means that whenever the state in there changes, it thinks that the whole thing needs to be invalidated. I'm just going to be cautious and just recompose everything there. But if we look further, we are just literally like passing the value from the swipeable card to the card, and internally it just is being used in the modifier. So, I mean, we don't need to like technically read the value right there. We are just, the value is being just passed and used somewhere else internally. So, yeah, I think with that wisdom in mind, Tasha, do you want to try it out and see if the book works and is magical?
I don't know how you found this book. I'm glad you did, and we're going to try it out. So the first thing you mentioned was using Lambda modifiers instead of what we were using already. Okay. So yes, we are using offset and graphics layer because we are dragging the card around, changing X, Y. We're changing the scale of certain cards and maybe the rotation as well. So let's try using the graphics layer Lambda modifier. This is a little shortcut we set up to save some typing. Now, what we're doing here is essentially all this is now here. So we can get rid of this old modifier. And also the offset modifier is just changing the XY position of the element. And that can really just be done by the translation X and Y properties in the graphics layer modifier itself on the graphics layer scope receiver that we have. So we can get rid of the offset modifier entirely. So what we're left with is just the one graphics layer modifier that's doing all the work for us, which is nice.
And that's the first wisdom.
That's the first tip from the book, yeah, the wisdom. So the second thing was to defer state reads as long as possible. So let's go back to where this card is, a swipeable card is called. So we have two parameters here that we can draw our attention to. And these item size and other sort of values here and states here are coming from, again, a state object that's read all the way over here. So there is a lot going on where literally the state reads are happening on these lines and they're being passed as parameters into a swipeable card. So if we can just defer those state reads to exactly where they're needed, that would be great. So let's actually do that. Let's turn these two parameters into Lambda parameters. So we have a little shortcut for that. So now these are Lambdas. And let's fix the call sites here. Let's go deeper into this other custom modifier we have. And since we're actually passing in this in here now, we need to call it in that modifier. So let's do this here as well. All right, so this is all green here, no red. Let's go back to the call site and fix it here. Let's use our handy shortcut, surround with Lambda. Okay, so now instead of these operations happening inline, they're actually going to be happening here inside the graphics layer Lambda, and then also down here inside this other modifier. Okay, so let's actually give this a whirl and see if we don't get those hundreds of recompositions every time we drag.
That means that we're just delaying it, right? Like the state reads.
Yeah, exactly. And in fact, the delay is kind of compounded because we're actually passing it into a Lambda that's read further down the line. Okay, so this is loaded. Let's go back here. Okay, let's try giving this a whirl. Okay.
Slightly better.
I see one. Yeah. Okay, I'm going to let go now.
Okay.
And let's see if I see.
The drag looks better. Maybe try swiping as well.
Yep.
Okay. I mean, the number is less for sure. And I think the lag you see is coming from the layout inspector. So we will definitely detach it to show you how it looks.
But yeah, I don't see like, like 50, 60, 100 recomposition.
Yeah, at least the recomposition is down.
Yeah. But there still are some recompositions, but it's a lot better.
But wait, I see there is like a gamepad overlay, which is also recomposing. That's weird, right? I mean, they're not changing that.
Huh. That is weird. Okay, so let me swipe a card. Actually, you know what? Let's just reset it so we can see everything clearly. Okay, I'm going to swipe a card. Okay, it says 1. I'm going to swipe another one.
Just one more.
It's just 2. Okay. That's weird, and we'll tell you why it's weird. So the gamepad overlay is literally just this row of buttons. We're not tapping on them. They're not changing in any way. But for some reason, this gamepad is recomposing. Let's take a look at the code. Okay, so here we have some logic. Essentially, if the cards are not empty, then we show the gamepad.
That looks correct to me. I don't know, like compose.
Yeah, I don't know what's happening. So when I swiped cards away, the list of cards is never empty. It's always non-empty. So like this conditional technically shouldn't be changing. Right?
Yeah, it doesn't need to recompose or draw it again, right?
So what's going on?
I know, like I've been like facing this issue so long. Like I read a lot of like Medium articles, Stack Overflow, everything. But yeah, I just keep coming back to this book. This secret book is so good. It just has it all. And yeah, it has something about this as well. And it says to use derived state of to limit the recompositions. So let's look at like what that means exactly. So right now, as Tasha showed, like we have this state, and we're checking if the cards are empty or not. And if they're not empty, we show the gamepad overlay. So in our example, let's say we have card A and B and C. It should show the gamepad. And that so far looks good, right? And so what happens is that when one of the cards is swiped, we see A and B card left. And compose, since the state has changed, compose thinks that it needs to recompose. And this condition is still met that the cards are not empty. The gamepad overlay is essentially like all the phases are run again, and it's drawn again. So it's recomposing the whole thing. So the wisdom from the book here is to just wrap this state into something called as derived state of. So you're building a new state from this one. And let's call it show gamepad, this new derived state. So what will happen with this derived state is that when the cards are swiped, so essentially A and B are left, this new state is still true. That means the cards are not empty, and it hasn't changed. So compose notes that the derived state is still hasn't changed, and it doesn't need to recompose. So that way, we can avoid the recompositions. And when all the cards are swiped, this new state, show gamepad, will be false, essentially like hiding the gamepad altogether, and that's when like compose will recompose exactly as we expect it to. So with this wisdom, Tasha, do you want to try it out and see if that works?
That's great. I can't believe a book like that had information about derived state. That's pretty cool.
It's a secret book.
Okay, so let's start creating that new derived state. So call it show gamepad, and we use our remember. And I have a Copilot on, so it's going to do that. Thank you, Copilot.
Yeah.
Read my mind. We're going to take the derived state. We're going to replace this line here. And we're going to hit the value read. OK, so now we're taking this calculation, essentially caching it with derived state, you could say. And then we're just reading the cached calculated value instead of this calculation directly. OK, let's give this a try and see if our gamepad
or if the book is right or not.
Or if the book is right. I mean, don't follow everything you read in a book, guys.
Unless it's a secret book of spells or something like that.
Yeah, in which case, definitely do the spells, yeah. All right, so moment of truth. I'm going to swipe the card. We're going to pay attention to the gamepad overlay. Okay.
Okay, the cards are still recomposing, which is fine.
Card
it's still
stack
less.
Is changing, makes sense.
The gamepad isn't.
Oh, the gamepad's not recomposing. There's not a single number here. Let's try a few. Let's actually use the gamepad.
Okay.
There we go. Okay.
Yeah, book
so
works.
Book worked.
Nice.
This is great.
Do you want to like detach the layout inspector just so that we get the full performance? Because layout inspector, like Tasha said, has a slight overhead.
All right. So let's try doing this now.
Yeah.
Let's try moving our cards around. Okay. This, I mean, it feels a lot better. I don't know if it's translating on screen, but it definitely feels a lot smoother. All right. Now that we're talking about recompositions, let's see if anything else is recomposing.
I want to just ship this ticket. Let's just push the code.
I know, but I mean, that book really got me hooked on recomposition, so.
Maybe we can create a new ticket for this other task, if there's something, please.
No.
No? Okay.
We've been doing the same task. Okay. All right. Layer inspector is back on. Let's expand a few things, see if there's anything weird happening. Okay.
Maybe let's just check the whole app, if everything is looking,
Good point.
yeah, just out
Go
of
ahead.
screens. Okay, let's try navigating. Okay, how's that looking?
I don't know. I feel like there's a whole bunch of blue on screen, and I think blue means it's recomposing.
It's recomposing. Interesting. So the home page is recomposing. It shouldn't, right? Like we are just showing like 3 tabs in there, not the color of them, or the state is not changing. We're not adding a new tab or something in there. So
yep. Every tap I do, home pager is recomposing. Okay, let's see what's going on. So we will minimize the layout inspector. Okay, so the home pager is a simple enough composable that contains the horizontal pager for the app, for the main scaffold of the app. I mean, there's not anything crazy going on. We got pages, modifiers, some state. Our pages are like pretty static, like 3 pages, nothing's changing. I don't know what could be recomposing.
Yeah, that's true. I mean, the list is immutable, right? Like we all know the list is immutable, so
yeah, we're not
nothing is changing in there.
Was there anything in the book?
I mean, I think that was all in the book, but I did see some missing pages. I don't know, does any one of you have those missing pages by any chance?
Oh my God. Okay.
Don't tell me, Tasha. You stole them?
I found something that might help.
Okay.
Okay, they might be the missing page.
Okay.
Okay, you ready?
Ready?
Okay. I mean, this is some pretty advanced stuff.
You easily blew that page on the.
Yeah, we just scanned it, the page as it is. It's all crumpled up. Yeah. I mean, that book was old.
Of course.
So composed compiler metrics is what you can turn to when things are happening and there's no obvious reason why things are recomposing or why pages are being invalidated even when state isn't changing technically. So compiler metrics is essentially a way for you to peek under the hood to see what the composed compiler thinks of your code. And in particular, what kind of parameters it thinks are stable and what parameters are unstable and when it thinks state can or can't change. So by default, compiler metrics are not actually going to be generated. In order to generate them, you're going to have to add some boilerplate. And specifically, the first piece of boilerplate you want to add is to kind of tell it where you want the compiler metrics reports to be generated. And then you want to ideally wrap all this logic in like a build flag, so you can run it only when you want to on demand, and you're not running it when you're like releasing your app to prod. So here we have the composed compiler reports flag. You can call it whatever you want. And the command that we want to run is assemble release, so that we can actually compile everything and make sure we're compiling the release flavor so you don't have any overhead from the debug flavor. And then finally, we want to specify rerun tasks. This is kind of important because we don't want to be hit with any build cache issues or incremental build issues. So we make sure we compile everything when we generate these reports. All right, so Akshay, do you want to dive into the reports?
Oh yeah, let's try this wisdom from the book and the page you stole, Tasha.
I didn't steal it.
Are you sure? Okay, it's cool. So in order to save some time, we have already run this command, which Tasha was talking about. So let's go to see what's the output. So usually the output is generated in the app module build compose metrics. And in there, we have, since we have already run it, let's just go in this text file, composable.txt. Let me minimize this. So the problem is with the home pager, right? So the home pager looks innocent, like a restartable, composable, home pager. There are 3 parameters. One of them is unstable. 2 of them are stable. I don't get it. Like, why is a list unstable? Shouldn't be it's stable. It's weird, right?
Okay.
What do we do?
Let's try to break this down a little bit. So what we're seeing is happening is every time we change the page, well, the compiler obviously thinks that the list of pages themselves, that piece of data is unstable. And so even if we just tap on a different page, because it sees that that parameter is unstable, it's actually going to cause the entire composable where the parameter is passed into to recompose. Because for some reason, it can't guarantee that nothing has changed.
Interesting.
Now, we might ask why it thinks it's unstable, and I think if we look a little closer, we'll see why. So the list, the parameter itself is of type list, which is an interface. And the list itself can be implemented in many different ways, including as a mutable list.
I didn't realize that.
Exactly. So Compose can't guarantee that list will never change, so it must err on the side of caution and assume that things can change and might have changed and recompose the composable where this is passed into. But we know it's not going to change, so we have to find a way to enforce that contract to the compiler. And to do that, we'll use the call in immutable collections library, and we will use the immutable list type instead of list. And since the 1.4 version of the Compose compiler, I think all the immutable collections are supported, the contracts are understood by the compiler. So with the immutable list, we can kind of implement it using the persistent list off builder or any of the other variants. And this contract really tells the Compose compiler that you're not actually going to be changing these, or if you are changing them, you're changing them in a very specific way.
Interesting. So we have to tell to Compose that it's not going to change, it's immutable.
Yeah, it's not that smart yet, so we kind of have to tell it. So do you want to give this a whirl?
Yeah, that sounds good. Thank you. Let's go there in Android Studio. So home pager is the problem. Let's go there. It's in the home. So this is our home pager. So let's jump into it. So as we saw, it's a list. So let's change this to immutable list. Ooh, where is this dependency coming from? So let's go if we have
We
that
have
already.
added a dependency already.
Thank you, Tasha, for adding it.
Exactly.
Thank
so if you scroll down a little bit,
it's in here.
there you go.
Oh, yeah, I see it. Collection immutable. Perfect. Sweet. Thank you.
So you have to add that additional dependency.
Perfect. So we have the immutable list set up. There's an error here. Let's go here. So we are passing some home pages. So yeah, this is like a static list, right? So I think it doesn't take list off anymore. So like you said, we need to use persistent list off. Let's just delete that. And yeah, let's run and check if it's still recomposing and if the missing page is true or not.
All right. So while that's running, we actually did run the metrics again after this change. I mean, since it takes a while to run, it's a release flavor after all. We ran it already, and here's the saved output. So if we find home pager here, we'll actually notice that if we're using immutable list, it considers it to be stable.
Now it knows.
Now it knows. All right. So let's expand our elements here. And do you want to navigate?
Yeah.
See if we
Let's
recompose?
see if it even works. OK, so I'm changing the tabs. Let's do it.
Okay.
It's not recomposing anymore. That's perfect.
But we see a different number, a grayed out number.
Damn compose.
What is that? Okay.
Is that good or bad?
I think that's good because it's grayed out, but let's hover over here and see what it means. So this first column is going to show us the number of recompositions that did take place, whereas the second column is going to show us the number of recompositions that were skipped, which is a good thing. Because what we essentially signal to the compiler with immutable list is that you don't have to worry about it. It hasn't changed. You can skip recomposing it. So it essentially making it opt out of recomposing that composable.
Perfect.
So, and to kind of verify that idea, if you look closer into the report itself, you'll notice this keyword skippable. And this is exactly a reflection of what we see here with the numbers. So I think we're doing a good job here. I think we're done.
Yeah, it does look like that. Let's remove the layout inspector just to check it out. And you guys can be the QA here and just tell us like if this looks performing good enough and so that we can ship this code. So how does that look? Is it smooth? What do you think?
I think it's going okay.
It's looking okay. What do you guys think? Is it performing good? Can we ship this? Okay. Let's ship this code and create the PR, Tasha.
All right. So type. 2 minutes later. Here's the PR. Okay.
Yeah.
So just to kind of recap all the fixes that we did so far. First up, we kind of created our own lazy card stack almost, where we made sure to not measure or lay things out if they weren't really needed. And then we use derived state of, thanks to the book, to limit recompositions that were based on state calculations that really just needed to be cached. And then two of the other related fixes were we used lambda versions of modifiers for frequently changing data, and the frequently changing data in this case was our pointer. So we were dragging the card around, that data itself is changing. Instead of using the regular modifiers, using the lambda ones really helped. And then sort of an extension of that, we deferred state reads into the modifiers themselves. So we weren't reading state regarding the cards and other things right up at the call side of the card itself. And then lastly, the idea of being mindful about state stability. We saw recompositions. We didn't know why they were happening. We checked compiler reports and figured it out. All right,
Perfect.
so
the PR is up.
PR is up.
I'm up to review it.
Okay.
Perfect.
Will you approve it?
Yep, let's approve it.
Okay, let's do it.
Gosh, Lucas. He says, hey team, could we verify if this fixes the performance issues using some data? Why does he want data? I mean, it's already good. Like you all guys also said, QA said yes. And he wants data which we can quantify. Thanks, and let me know if you have any follow-up questions.
Okay.
Lucas, damn it.
Lucas is our manager. He always does this. He always leaves comments on our PRs. Anyway, but you know, I don't think I can argue with him though. I think he's right this time. Like we saw it with our naked eye, but is it really doing any better?
Yeah. I mean, the executives need the number, right? Yeah.
We need numbers. All right. But luckily, we did have a macro benchmark test. And we did have a run that we captured before the fixes. And we didn't capture it live here today, but we did capture a run with all these fixes included. Now, we noticed that the before run, we have sort of numbers in the 60s, 70s, and 90s for the average and worst frame overrun time. So these were exceeding the deadline by a lot. After the fixes, they were reduced somewhat, but they're still positive and they're still kind of high. So it's not perfect, but it does indicate some type of improvement. And if we just kind of measure the diffs here, we see about 40 to 30-ish%. And take this with a grain of salt. Like, this is obviously something you want to be a little statistically rigorous about. We just ran it on one device, you know, a few iterations, just to kind of give you a sample of how we could do this. So to summarize, the P50 gain, which indicates the average frame, the rendering times are 40% quicker-ish. For the P90s, the worst performing frames, we achieved a slight boost of around 30%. This was with a Pixel 3a, so that was pretty
like
gnarly.
6-7 years old phone,
yeah,
I guess.
Exactly.
Yeah.
All right. So just to kind of summarize what we did here today. So whenever you're faced with performance issues, the first thing you want to kind of tackle is kind of pinpoint where they're happening, what screen they're happening on, where in that screen they're happening. And you can use the profiler, you can leverage system traces, make sure to introduce the composition tracing library so you see detailed information about your composables. And then for numbers and more sort of objective information, you can use, if you have a manager who likes data, you can use the frame timing metric and write a macro benchmark test to measure frame rendering times. Once you're past that, you might say, okay, well, I know where it's happening, but why is this happening? Why do I see janky frames?
Yeah, what is happening, like, under the hood?
Exactly. And usually it is related to recompositions in the case of compose, such as in this very specific example. And you can use the layout inspector and look at the recomposition counts to really pinpoint how bad the recompositions really are, the unnecessary recompositions. And then lastly, if you've done all that, and you've followed the best practices, like as we saw in the book. By the way, we think the Google team got a hold of that book, and so all that information is on the developer page right now. So it's great.
Yeah.
So if you've done all that, you followed best practices, but you still notice unnecessary recompositions, basically things that are not obvious to you, then you can turn to the compiler metrics and get an under-the-hood glimpse of what's going on. And then finally, once you're done with everything before you ship the changes, definitely test with a release build and attach the profilable flag in your manifest. This will make sure you're running on a release build so it's closest to what the user will see in the wild, but then also the profilable flag will enable you to use the profiler on your release version, which is really cool. All
awesome. Right? Yeah. Okay. Thank you so much for listening to our talk. Yeah, and yeah, feel free to